Hello students and welcome to the lecture on Stochastic Universal Sampling. The 15th lecture in the lecture series for the course of Introduction to Soft Computing for Electronics and Telecommunication Engineering students of the 7th semester Goa College of Engineering. I am Ms. Purti Savardekar, the faculty in charge for this course. In the last lecture, we discussed and understood the roulette wheel selection operator. In today's lecture, we focus our attention to the next most commonly used selection technique, the stochastic universal sampling technique. Let us begin. Firstly, do not be intimidated by the name of the method. If we understand the meaning of the words properly, we will be less fearful of it. Stochastic, in simple terms, means random. Sampling is the process where a certain number of observations are taken from a larger population. Universal sampling is where samples are being picked up from the entire population, not just some portion of it. So, stochastic universal sampling by name could be thought of as the process where individuals are selected randomly from an entire population. Although this seems slightly vague right now, we will try to understand this method a little better in this lecture. The short name for the method can be sus, and you may remember it as that so that it sounds a little less intimidating. Because the method is actually based on what you have already studied in the last class, the roulette wheel selection. So, we already know a part of the method. At this point, I would request you to watch the roulette wheel selection technique video, maybe at twice the speed for revision, and then return to this video. So, as you must have seen, in the roulette wheel selection, the size of the pocket is made proportional to the fitness value or the expected value of the individual. Obviously, then, a fitter individual has a higher probability of being selected. The problem that this technique faces is that it is very likely that the high fitness individuals keep getting selected over a number of generations and become a majority of the population, while the lower fitness individuals do not get selected at all, thus killing the diversity in the population and possibly achieving a local peak of fitness instead of a globally optimum solution. The fitness proportionality in the selection process itself, becomes a curse. In this process, we also assume that we select one parent. Every time we run the algorithm, one parent is selected. To improve the algorithm, we may vary it a little bit and choose more than one parent at a time. That means instead of only having one pointer in the roulette wheel, we could have 2 pointers for selection of 2 parents, like this. This means that we are selecting 2 parents in the single run of the algorithm. The pointers need to be spaced appropriately. To understand and visualize this better, let us roll out this roulette wheel into a line and analyze. If this is possible, then we can have even more number of parents selected by having more pointers spaced appropriately like this. The individuals corresponding to fitness values pointed to by the pointers are the parents selected for the crossover. That is what is SAS, stochastic universal sampling, the process where individuals are selected randomly from the entire population. I know you will have a number of questions. How is it random if the samples are appropriately spaced? To understand stochastic universal sampling better, let us consider the same example that we had considered in the last video. In this example, we have considered 6 individuals A, B, C, D, E and F, each with their respective fitness values 8.2, 3.2, 1.4, 1.2, 4.2 and 0.3. The roulette wheel then is designed in a way that the pocket for each individual is proportional to their fitness. Then a fixed point is considered and the wheel is spun. The pocket at which the wheel eventually stops is the individual who is selected as a parent. This is the roulette wheel selection technique. Our sus technique is very similar, but As we said before, instead of selecting just one individual, sus allows us to select multiple individuals in a single rotation. How? By having multiple pointers. Let us assume that we want to select two individuals. That means we will need two pointers like this. If one pointer is placed here, the other pointer is placed exactly on the opposite side of the roulette wheel. Then the wheel is spun. It will stop randomly at some location. The individuals at the pointer locations are selected. Now consider the same wheel but with three pointers like this. The pointers are placed at uniform distances, but the rotation stops randomly and selects three random individuals. This number of individuals, the number of pointers, may be whatever we want. I hope the idea is clear. Now, for us to be able to develop the pseudocode, it is vital for us to see an example where the roulette wheel is rolled out into a line like this. Pause the video for a minute or two and try to observe the example. The number on the line segment from 0 to 1 is the total probability, which is further divided into 10 smaller line segments. That means there are 10 individuals in this population. Notice that the size of each smaller line segments is not the same because it is dependent on the fitness values of the 10 individuals. This is the rolled out fitness wheel. Now concentrate on the pointers. There are 6 pointers. That means 6 individuals are being selected. Most importantly, notice how they are placed. They are placed at equal distances. What does that do? A combination of two changes in the original roulette wheel selection algorithm. Firstly, the possibility of having multiple pointers or selecting multiple individuals, and secondly, having equally spaced pointers has improved the chances of weaker fitness individuals to be selected. Pause the video for a minute or two and find out the individuals who have got selected in this case. Find out? Go ahead, give it a try. Yes, in this case, the individuals that are selected are 1, 2, 3, 4, 6 and 8. If the selection method was roulette wheel, then it would have been highly possible that because of a single pointer, for all 6 individuals to be selected, one by one, most of them would have been higher fitness individuals. I hope this example has cleared any doubts if you had. Now pause the video for a minute or two and think about this. Where is the randomness in this example? Where is the randomness in this example? Go ahead, give it a try. Although the roulette wheel is now represented as a straight line here, the array of pointers which looks sort of like a comb, it has to move through the entire line segment as if it is joined back to back, and it has to stop randomly. The place where the comb stops decides the individuals that are selected. That is where the randomness lies. So if you observe, we do not have to randomize all the pointers. Instead, the randomness lies in the position of only the first pointer. The remaining pointers are spaced appropriately, uniformly from the first pointer. So, having only the first pointer as a random value is sufficient. Remaining pointer positions can be then calculated with respect to the first pointer. Now I hope the meaning of sus is justified. Stochastic universal sampling. Stochastic universal sampling. So as we have seen, roulette wheel is biased towards high fitness valued individuals, and sus is an improvement over RWS, roulette wheel selection. I hope the content covered in this video was clear. Let us now continue the discussion in the live Google Meet. See you there. Thank you.